Welcome to the channel. In this video we're gonna go through this question which summarizes all three modes of heat transfer and the three modes which are conduction, convection and radiation. So let's go ahead and solve this problem. The first thing that we have to do is understand what they're asking us. So we have this one plate and then second plate, right? And then the temperature in this plate is 300 Kelvin and temperature in this plate is 200 Kelvin. And so we have four cases. The first one is if this empty space is filled with atmospheric air. The second case is if the space is evacuated, which means if this is a vacuum. And the third case is if this space is filled with urethane insulation. And last is if it's filled with superinsulation. So let's go ahead and solve the first case. A. Filled with atmospheric air. What does this mean? It means that we have, out of three modes of heat transfer, we have two of them, which is conduction and radiation. So the formula for conduction is Ka surface, T1 minus T2 divided by the thickness. For this one, what is K? Well, if you look at this table that I have right here, for this, the value of K depends on the temperature, right? So it means that we have to find the average temperature because we have one here, so we have to find the average. And the average temperature is 250 Kelvin. If we convert it to Celsius, we just have to subtract 273 from this, which becomes 23 degrees Celsius. So the value of K at negative 23 degrees Celsius, if you look, we don't have a negative 23, we only have negative 30 and we have negative 20. And for negative 30, we have a K value of that. For negative 20 Celsius, we have a K value of that. Now to find the K at negative 23, we have to do interpolation. So let's just start. Negative 30, negative 23, negative 20, right? And for negative 30, we have 0.02134. For negative 23, we don't know, so let's just call it X. Or K, it doesn't matter. And for negative 20, we have 0.02211. Okay, so negative 30, negative 20, divided by negative 23, negative 20 equals 0.02134 minus 0.02211 divided by X minus, 0.02211. So this is a simple algebraic equation. So we have to solve for X. And once we do that, the value of X, or K, right? Because we are actually looking for K and this X represents K. The value of K is 0.0219 and the unit is watt over mK. So that's our K. Now we know K, right? Do we know the surface area? Well, we can make assumptions because in the question it doesn't say what is the area. So we can assume AS is just 1 meter square, right? 1 meter, yeah. Area of this plate is 1 meter square. So now we know AS, right? We know K, we know T1, we know T2, we know delta X. And delta X, which is this L here, which is this L equals 0.01 meter. Okay, so now let's just solve for conduction. Q dot conduction is K, we have 0.0219 multiplied by area multiplied by T1 minus T2 divided by 0.01. and this gives us a value of 219 watt. Now that's for one of them, and then we said we have conduction and radiation as heat transfer. So for Q dot radiation we have, well, a formula for radiation is epsilon sigma A T1 to the 4 minus T2 to the 4. And we are given, we know the value of epsilon, right? Because it's given here. Epsilon emissivity equals 1. And sigma it's Stefan Boltzmann's constant, which is 5.67 times 10 to the negative 8. The units are m squared, k squared. Okay, and we know that, we know A's, we know T1, we know T2. So let's go ahead and solve for Q radiation. And if you just plug in the value that we have here, 1 times 5.67 times 10 to the negative 8, 1, right? 300 to the 4 minus 200 to the 4, and Q radiation, for that we have 369 watt, and the total heat transfer rate is just the sum of radiation and conduction, which is 369 plus 219 and equals to 588 watt. So that's for our first case. Now for the second case, they're saying that if this space is evacuated, aka vacuum. Is it how you spell vacuum? Nah, never mind. Okay. And if it's vacuum, it just means there is no conduction. There's nothing between them. So it's pure radiation, right? The heat transfer between these two plates, if it's vacuum, is pure radiation. So formula for pure radiation is the same thing we have here, right? And basically it's this one, because nothing changes, right? They all stay the same. So 369 watt, which is the Q total. That's it. For case C, they're saying that if it's filled with urethane insulation, because it's insulated, there is no radiation. It's only conduction. So this is pure conduction, okay? Why it's conduction? Well, we have one plate, we have two plates, right? And this space is filled with insulating material, right? So they are directly connected by insulating material, which conducts heat through them to this other side, right? So we start heat from somewhere here, and then heat decreases to somewhere here, right? T2, T1. That's it. No radiation, no convection, pure conduction. Formula for that is conduction, which is the Q total, okay, is K A T1 minus T2 divided by L. That's the formula, yeah. And we just plug in the data, but first we have to find what is K. Sorry about that. First we have to find what is K in this case. Well, if you look at a table that I'm gonna paste, hold on. Okay, so from this table we see that urethane right here, okay, the value of K is 0.026, and this is at a mean temperature of 24 degrees Celsius, which is fair because we are at 300 Kelvin, which is equal to 27 degrees Celsius, right? So it's fine. We can use that. So 0.026, we said A is 1, 300 minus 200 divided by 0.01. And for this case, we have a 260 watt. So that is our Q dot unit of total heat transfer. Now for the last case, we have a superinsulation. And again, this just means it's purely conduction, okay? And then we write down the same formula, okay? Q dot conduction, Ka T1 minus T2 divided by L. Write down the same formula. And we know the value of K because they say that K is K equals 0.00002 mk, right? So we know K, we know A, we know T1, T2, and L. Just plug in the values and we get the total rate of heat transfer for superinsulation, which is simply 0.2 watt.